And to be honest with you, I'm not too concerned. We're going to spend 15 minutes a day on it. We're going to spend maybe about 15, 20 minutes tomorrow on it. There won't be a huge amount of questions on your tests about it directly, but there might be some things that you can use. What I want you to understand is that everything that we learned in Sem 5, you have already learned. You already have an alternative way of dealing with these things from just basically knowing your angle-angle similarities and side-side-side similarities and side-angle-side similarities. Okay, so you have all the tools already necessary to solve any of the problems that I would give you in this section. Okay, so we'll spend a little bit of time on it, but not a drastic amount. I've got this. It's called the triangle proportionality theorem. Okay, and we're going to go through a little bit of the algebraic proof of why this thing works. Okay, basically what it's saying, guys, is if I have this segment X and this little segment here, so that one's Y, that little one is X. Okay, this one here, use a different color. This one, maybe I want to call that Z, and I want to call that one W. What the triangle proportionality theorem says, as long as these lines are parallel, they have to be parallel. If you don't have parallelism, then things are broken up proportionally. But what it says is that you can take X and you can compare it to Y. Use those letters, that color. X compared to Y. And then in the same order, so I went top to bottom, right? X to Y. We'll come over here, top to bottom. It's going to be Z over W. And what's nice about that is that distance right there, is that part of a full triangle, or is it a full side of a triangle? No. Okay. This red part is, that's a full side of a triangle, right? Or that top triangle. But the blue is just part of that segment. Okay. But the proportionality theorem says that this will be true. Okay. So what I like to do, what I like to think about kind of visually, is that when I'm comparing them, I'm going to circle that one, draw an arrow to that one. So that's my ratio, X to Y. So then I should follow the same order over here. Circle that one, Z to W. Does that make sense to everybody? And you can flip them. You can start at Y and go to X, because we can flip proportions. But can't we flip these things? Can I flip Y and Z? Because they're the means, right? So I could write this as X compared to Z is equal to Y compared to W. Kind of look at the order that creates. X jumps over and compares to Z, the top part compared to the top part, right? Y jumps over and compares to W. Bottom part, jump over, compare to the bottom part. Does that kind of make sense to everybody? So some of you might like the kind of the vertical alignment, X to Y and Z to W. Some might like the horizontal alignment, X to Z, Y to W. Any one of them is okay, because we know once we set up one of them, we can interchange means. That's a proportion property that exists, and we should still get a true proportion. All right, so let's prove this. Let's talk about why this happens this way. I'm going to call this C, D, A, E, and B. Okay. If these two lines are parallel, would you guys agree that there are two triangles here, right? Would you agree that that angle, C, is in both triangles? Okay. Would you agree that that angle there is congruent to that angle there? So we have angle-angle similarity, right? Okay. So I'm going to talk about these triangles as, let's just say ABC, and say that that is similar. So A to B to C needs to be similar to what? D, E, C. Is that okay? A to B to C, and then D to E to C. Okay, so now we should know. Okay, if you ever see those three dots like that, that stands for the word therefore. So therefore, AB should compare to DE, and that is going to be equal to BC compared to EC, which should then be equal to AC compared to DC, right? Is that all right with everybody? All right, so every question that we do in this section, that is the tool that you could use to solve it without knowing this section. Does that make sense? You can use that relation. Now, to prove why the theorem that we're dealing with works, I'm not going to be concerned about DE and AB because the proportionality theorem didn't talk about DE and AB, so I'm going to get rid of this ratio. But we know that these two ratios are true, right? Okay. Let me see if I can move things up. And no, it's not going to work. Just for the benefit of this problem, actually, never mind. It's going to be okay, I think. Yeah, should be okay. Last class, we had to take the reciprocals just to make things make sense. Algebraically, what I want to do is see if we can manipulate this so that I'm able to get this portion compared to that portion. Okay? And if I'm able to do that, that will create that portion eventually compared to that one. Okay? So the way we do this is we take BC. BC, using the segment addition postulate, could we say that this BC could be rewritten as CE plus EB? Everybody okay with that? And then this EC, I'm going to leave as EC. Now on the right-hand side, would you guys agree that that AC could be rewritten as AD plus DC? AD plus DC is okay? And I still have this DC on the bottom. So this blue proportion and this red proportion are the same thing, right? Okay. Now I'm going to do something over here on the side with some numbers to prove a point to you. If I have 2/3 plus 5/3, what can I write that as? 7/3, right? Or 2 plus 5 over 3, correct? Okay. This right here, now I don't know what the numbers are. I don't know if that's 2 or if that's 5 and that's 3. I don't care. But do you see how that format that I put this box around is the same format you have here? And this is an equation up here. So couldn't I start with this, start with a common denominator essentially, and break it up into fractions? So why can't I do that here? Why can't I take CE plus EB and write that as CE over EC plus then EB over EC? Does that make sense? If I added those together, do they have a common denominator? And I would just add the numerators, and that gets me back to this thing here in red, right? Do the same thing on the left, or sorry, the right. Can I go AD over DC plus DC over DC? Okay. Now think about this. What is CE divided by EC? That's 1, right? That's something divided by itself. So I'm going to replace that with 1. What's DC divided by DC? That's 1. If you have 1 on both sides, they cancel each other out. And you're left with EB. Okay, so let's look at this. Let's EB. This was B, C, D, and E. We've got EB. So let's call that W. Compared to EC, let's call that Z. Can we do that? And then AD, I think we had that called Y earlier, right? And DC called X. So we're comparing this little part to that little part, and then that part to that one. Does that make sense to everybody? All right. what I want you, and I think it's important that you guys see that. You see that kind of generic algebra with those generic parts. Understanding your rules of algebra and how you can break parts up with fractions, stuff like that. Because it provides you insight on essentially how most of the things that you guys are provided in a math class as facts or theorems or definitions, whatever, how they're created, how we know them to be true. So we're able to go through little, that's a proof, we're able to go through little proofs like that. Okay? And it develops this relationship that will always work no matter what triangle I'm in, as long as these two parts are parallel. That has to be met first. Okay? So that being said, let's do a couple examples here. I'm not gonna do the algebra with you. We'll just do the geometry, setting these up. What do you take 33 and compare it to? Compare it to x. So if I put 33 to x, I'm gonna go 27, 18. That's pretty easy. Okay. Is it okay to do this? Flip-flop the means and say 33 compares to 27 as x compares to 18, because that's going from here across and then there across, right? Can I take the reciprocal of that one? I should be able to take the reciprocals of either side, or both sides, right? All that would do is get me to look at basically taking 18 and then compare it to 27, and then x compared to 20 or 33, right? Does that make sense, everybody? And I can take the reciprocals of the blue one too, and all that's going to do is basically change the direction. Start on the right, go to the left. Start on the right, go to the left. Really, the only thing that you guys cannot do that will not produce the correct answer is to take 33 and compare it to 18. Does that make sense? Okay. So take 33 and compare it to either x or 27, and then with the things that you're left over with, try to mimic the same pattern. What about this one? X to 16 equals 9 to 12. Okay? Now think about why this works, guys. And going back to what we did in the chapter earlier, you know that that's 9. You know that this is x. This would be, I'm going to write it as 12 plus 9. I'm going to write this as x plus 16. Does that make sense? These two triangles would be similar by angle. All right, so they are set up in the right orientation to where I can say 9 compares to 12 plus 9, and x compares to x plus 16. Okay? We can subtract or add versions of 1 to that. Okay? So can I take... I guess what we said was we take the denominators and add it to the numerators, right? We can do that. Okay? I can take this denominator and add it to that numerator. If I do that, I get x plus 16 over 16, right? Take this denominator and add to that numerator, and I get 9 plus 12 over 12. Do a little bit of reciprocal work. Are those two things I put boxes around the same thing? Yeah. So if those were the same thing, and I was able to get this one from that, hopefully you realize that this is an approach that simplifies things for us. It's a theorem that allows work to be done a little bit easier than maybe what we were able to do earlier in the chapter. Okay? So 9 compares to 12, x compares to 16. You can say 9 goes to x, just like 12 goes to 16. Okay? Now, generally speaking, obviously they start you off with some easy ones, but they get harder. Okay, because they make you do a little bit of preliminary work before you start comparing stuff. What would that distance right there be called? It's the total minus the part, right? The total is x minus the part that you know of 15. So now 15, what can I compare that to? Okay, x minus 15 I heard. So what would have to go over here then? 20 to 8. What if I said 15 is going to go to 20? What would I put over here? X minus 15 over 8. Okay? And once we develop those, then the algebra that we've talked about all chapters starts to kick in, right? Okay. So a lot of these are pretty similar. Tomorrow we'll start off on slide 9 here, and it's just it's a direct conclusion of what we just talked about, because there's a triangle in there that we can focus on and get the same as that last statement, that last theorem. Remember, like I said, there's 3 assignments available.